In this video, we are going to solve a radiation problem. The problem is telling us that we have a surface A1, which is a diffuse emitter, which means that radiation is emitted in every direction equally. And we have three more surfaces like this. This is A2, A3, and A4. And it tells us the distance between each surface. And it says that this angle is 60 degrees and this one is 45 degrees. And it also says that A1 is equal to 10 to power minus 3 square meter, and A2 is equal to A3, and A3 is equal to A4, and they are all equal to 10 to power minus 3 square meter. And it tells us that the radiation intensity is equal to, which we showed by IN, is equal to 7,000 watts per square meter stratton, which is the angle unit for spherical coordinates. From previous lecture, we know that dq is equal to I lambda phi theta dA1 cosine of theta sine of theta derivative of theta derivative of phi. And now here, because A1 is a diffuse emitter, so our problem is not dependent on phi and tau. So we can, and because these surfaces are too small, we can say that Q is equal to A1 times cosine of theta times sine of theta derivative of theta derivative of phi. And we know that omega is equal to, derivative of omega is equal to dAn divided by r to power 2. So we can calculate d of omega for every surface. For example, between 1 and 2, we can write omega 2,1 equals to the surface that is perpendicular to this line, which is equal to A2 cosine of 60 divided by r, which is this line, and r is equal to 0.5 meters. So this is 0.25. And if we do this calculation, we see that omega 2 is equal to 3.46 times 10 to power minus 3 stratton. In order to calculate the rate of heat transfer between surface A1 and A2, we can write Q equal to I times A1 times omega 1, 2, 1. And this is from surface 1 to surface 2. So Q1, 2 is equal to, as we said before, I is equal to 7,000. A1, we said it's equal to 10 to power minus 3, and omega 2,1 we calculated as 3.46 times 10 to power minus 3. And this is equal to 12.1 times 10 to power minus 3 watts. And this is telling us that by only the means of radiation, surface 1 is emitting 12.1 times 10 to power minus 3 watts of power to surface 2. Now, we can calculate the same thing for surface 4 and 3. So, for surface 4, we have omega 4, 3, which is equal to the perpendicular surface to this line, which is A4, because this line and this are perpendicular. So here we write A4 divided by minus 0.25, which is equal to 4 times 10 to power minus 3. And for calculating the rate of heat transfer, we can write Q14 is equal to I times A1 cosine of 45 times the omega, which is 4 times 10 to power minus 3. And Q14 will be equal to 19.8 times 10 to power minus 3 watts. And you might notice that we have considered I equal for all of these surfaces, and as we said at the beginning, surface A1 is a diffuse emitter, so the intensity of radiation in every direction is equal, so we can use the same I for finding the heat transfer in every direction to every surface. Now, if we want to calculate the rate of heat transfer between surface 1 and 3, we first have to again calculate omega 3.1, which is equal to A3 divided by 0.25, which is equal to the same, equal to omega 4.1, which we calculated as 4 times 10 to power minus 3. And rate of heat transfer from surface 1 to surface 3 is equal to I times A1 cosine of 0, because these two surfaces are parallel, times omega 3.1, which is equal to 4 times 10 to power minus 3. And this heat transfer is equal to 28 times 10 to power minus 3 watts. So we learned how to calculate the rate of heat transfer between surfaces in a situation which we have a diffuse emitter.